Hello, everyone. I am Rytis. I'm a programmer at SneakyBox, and today I'll be talking to you about optimization. A high-level overview, somewhat a broad introduction to how things work, why you should care, and what are useful things to know when doing optimization work. So, the things I will be talking about are not exactly new. A bunch of people have talked about them before. So, for example, Mike Acton or Fabian Giesen or Casey Muratori. So, if you're interested in optimization kind of things in performance programming, I highly suggest you check them out. Check their videos out because they're really well done, well made, and well explained. Things I'll be talking about will be like various things picked up from either these videos or various resources I have come into throughout my years of programming. So yeah, and throughout this talk, I'll try to answer a few questions. For example, why should you care about programming, about performance programming? How does optimization work look like? And what things you should know about when you're programming for optimization for performance-heavy environments, right? So for the first question, why should you care? Maybe your answer is that you don't care. And from my anecdotal experience, I could tell you that, well, there are various things that you might run into, right? In my personal experience, I've run a bunch of times into issues with Visual Studio when searching for various strings, which takes, for some reason, a very long amount of time. And then maybe you're working with Unity, and then Unity is compiling a single shader for multiple hours, and it's taking a long time. And then maybe you look at people like Google, who have throughout time increasingly run into problems with compilation times and compilation steps, multiple compilation steps taking multiple hours to compile. And then maybe you are just a simple PC user, and then you try to do something in Windows Explorer, and then it stalls forever, and then eventually crashes. So um, these are various things I have run into personally throughout the time I've been programming. And if you haven't, maybe you are not as aware of these issues. But if you are and you still say you don't care, my answer would be, really? Like, these are pretty annoying things to deal with on day-to-day basis. And even some people, one of which I've already mentioned, have somewhat of a ranty videos made about these things. For example, Casey Muratori or Jonathan Blow. So if you're up for some entertainment and or ranty perspectives, which are, by the way, quite true, then I suggest checking them out as well. But let's say that you want somewhat of a more pragmatic view, something maybe you could go to the lead and talk about, or maybe a project manager and tell them that this is an actual problem that we should look into. Maybe you want to have some arguments about performance, but you have none. So I would pose that games, which probably all of you are familiar with, do care about performance. Now, if we look at Steam hardware survey, which is of this year's, it's a bit earlier one, but it's still relevant. So you might see that there is a lot of hardware that is actually pretty good, right? So you have at least like 4 gigabytes or 6 gigabytes of video RAM. Then there are a bunch of systems that have at least 8 gigabytes of system RAM, and then there are a lot of cores on most PCs, and these cores are actually pretty high frequency, so they probably run pretty fast, right? But one thing this misses on out is that the PC market is actually not the whole market of the games. So if we look at the whole market of the games of the recent years, bunch of it is actually mobile games, smartphone games. And well, I won't be getting into mobile games today, but it is just as relevant for them, even if not even more, right? Because usually smartphones have pretty constrained hardware, and they it is pretty hard to run certain things on them, and then they have batteries to care about and lifetime and all that stuff. So performance is important there. Though I'll be focusing today a bit more on the console side of things because I'm more familiar with that. I've been working with consoles for more than 3 years already. And what can we say about consoles, right? So there is some console data publicly available. The hardware specifications for last generation consoles. Let's for example, right? So we have Switch, we have Xbox One, we have PlayStation 4, and you could look at these specs and say it's actually not that bad, right? So you have like 8 gigabytes of RAM for PS5, Xbox One, half as much on Switch, 4 gigabytes, yeah, but it is not as bad, right? If you compare it to Steam Hardware Survey, it's like at the bottom line, but it's still there, right? So it's um, not as bad as you might think, right? But it's not exactly the whole thing because the even though like if we're focusing on memory, right? Even if you have 8 gigabytes of RAM for PS4, Xbox One, or Switch has 4 gigabytes of RAM, even less than that is actually available for your game because there's a operating system running in the background that has to manage things. And then if you look at into it a bit more, this memory is actually shared between CPU and GPU. So this is the whole pool that you have. So if you compare it to the Steam Hardware Survey, now it suddenly becomes that the last generation consoles are way below the bottom line, while at the same time they're probably a pretty big part of the market share. So if you need more arguments to say that you care about performance, right, that would be one of the better arguments, I would say. Now, uh, assuming that I made you think about performance a bit more, right, to care about it a bit more, how does that look like, right? How does performance work look like? Now, optimization is in principle diagnostics, right? Why? Because to solve a problem of optimization, you must first be sure that there is such a problem, right? You have to diagnose that that problem exists. And then if there is a problem, you must divine that the problem is somewhere, right? You can find it somewhere, and that what kind of problem it is, right? So basically, you need to diagnose certain things about the program you're looking into to make sure that the problem exists and then what kind of problem it is. And the best tool, at least the best currently available tools, group of tools for that kind of thing, for diagnostics, is the profiler. Now, there are a bunch of different profilers available. I won't be getting too deep into them. I'll mention a few things, but overall, the thing profiler does is it lets you look into how your program is running, right? How it looks like at the frame by frame, how much time certain functions take up, maybe how much memory certain allocations are taking, how the thread utilization is looking like, right? Maybe a lot of threads are idling, and then you could use that additional hardware, right, for your purposes for faster frame rate. And there are a bunch of profilers, such as I mentioned. This is one from screenshot from Superluminal. Then there's Intel VTune, and you can see in both of those, right, that they have like pretty grounded things to look at. They have actual times, actual function calls, function names that help you out to figure out what kind of problem you are facing. Now, you might be using game engines that have already some tools prepared for them. For example, Unity, right? Unity has its own profiler. It is pretty well tooled and shows quite a lot of things, which are actually very helpful for the most part. It has a memory profiler, which is less polished, but it still shows what it needs to show. Then there are frame debuggers if you are running into GPU issues and you're trying to check out specific draw calls that you know are less performant and what are they doing exactly, right? And then there's Heap Explorer, that is basically memory profiler, just on steroids, you could say. Like it's quite a bit better. Then if you're using Unreal Engine has its own profiling tools, right? It has its own profiler. It has Unreal Insights, which provides additional data. I believe it's more GPU focused as well. And then there are stat commands, which are various performance counters that show how your game is running, right? What's the average runtime of things, average allocations, or maybe some edge cases that you care about. And then if you're using custom engines, customly written C++ code, for example, then there are a bunch of profilers available for you. So Superluminal, as I mentioned, there's telemetry, Tracy, Intel VTune. There are probably more that I'm not as aware of. And these are for the CPU side of things, and there are a group of tools for GPU side of things. So RenderDoc is more of a debugger, but it can profile, I believe, AMD GPUs. And then there are like vendor-specific profilers. If you, depending on what GPU you are using, you can get NVIDIA, AMD, or Intel-specific profilers for your GPU. And then there's like, if you're using Windows and care about DirectX things, then you might look into PICs. So there are a bunch of tools to pick from, to use and try. And these are all actually very helpful when facing optimization problems. And using them is basically the first step in the optimization work loop, right? So you use a profiler to profile the program, to know where the bottlenecks are located. Then you figure out what is causing these bottlenecks, and you fix the issues. Then you profile again to see whether your fix is actually improving the situation or it made it worse, because it does happen sometimes. Yeah. And then finally, you have to make sure that the fixes you made did not actually break anything else. So it's kind of a fixing QA loop that is basically spinning for infinity, right? And you can do optimization work forever, but usually you have to stop at some point. So this is on the high level how that kind of work looks like, right? And now, what are the things that you might want to know when working on optimization things? So a bunch of tips will be pretty quick. If you care about some of them more, please ask the question after the talk. So yeah, first one is the fastest code is the code that is not running, right? So whenever you are faced with a problem, probably one of the first questions you should ask is, do I actually need this thing for my program to run well, right? So there is a joke among like more senior programmers that you start writing less code and basically deleting code, and this is what senior programmers do, because like that makes the program both a bit more cleaner and usually more performant. So there is a lot of people that echo such a sentiment, and it's pretty much true, right? So on its very basic logic level, it is true. Now, you might say, well, why not delete a lot of stuff? And in that case, I would say optimization is only relevant if you are making your programs still run correct, right? So if you're breaking things along the optimization path, it's probably not good, because your program will no longer be running correctly, or your frame will be like broken all over the place and nobody will want to play it. So this is a meme from XKCD. And this is basically what I'm talking about, right? You might want to optimize your random number generator, but if you make it return a static value the whole time, it will not work correctly anymore, right? It will be much faster, but it will not be correct. Another thing, which primarily Mike Acton, I believe, accents a lot, which is it is important to know your data and the transforms you are trying to do. So basically knowing the constraints and the context of the things you're doing, right? Why? Because fundamentally, the whole thing the CPU is doing is transforming some kind of data from one format to another, right? It is a simple thing of like, if you look it from very far away, and it makes total sense, right? CPU is something that is executing instructions on some kind of data, and it's everything that it's doing, right? So knowing the context regarding the transformations and the CPU environment you're running into is important, because there's a lot of things actually in there. If you would look at CPU like a black box, it might not be as useful. But if you know that there's like something called like a front end, right? Something that is decoding the assembly instructions CPU is passed, and then it is sending these instructions into an execution pipeline. And then there are different parts of the execution pipeline, and these ports can be actually used in parallel in some sense. And then there's like a floating point unit, which is separate from integer unit. And then you have the whole memory handling thing, which is basically a lot of caches in CPU, right? All this context helps you make better decisions about the transforms you want to do and how to do them faster, right? And then adding a layer on top of that, this whole CPUs thing is actually just a small part of like multiple cores, multiple CPUs, if you will. That is also important if you're trying to tackle performance problems. There's also like things like SIMD, single instruction, multiple data, which is another layer which helps even more to optimize for performance. So knowing all that stuff is actually important. And then there is a thing regarding the trade-off, right? So you cannot just get the cake and eat it too, right? You have to have some trade-offs and figure out things that like um, are important at certain parts of your program, because you will probably always will be doing a trade-off between memory and time. And when you have like a memory constrained environment, it probably means that you'll have to use less memory, which usually means that you'll have to have increased frame times, right? So it will probably be running slower. And nowadays it's mostly about memory, both in memory capacity, memory storage side of things, and like memory latency things. Because memory latency is actually pretty high, memory is rather slow to access from CPU, and if CPU is waiting on memory to retrieve the data to transform on for a long time, then it doesn't matter how fast it can run, it will be just bottlenecked by memory. So using cache is really important, and treat your cache as your best friend. Now, make sure that you know what is possible, right? There are some things that are maybe physically unfeasible on your hardware. So when you know, like, even a broad stroke hardware specifications of the hardware you're targeting, right? Do some back of the napkin calculations. So how does that look like? Maybe, yeah, I'm targeting Switch, right? I want to have a game of 60 frames per second, like, to not look horribly for the players, right? And then I went to have some kind of simple, very basic particle simulation for the game. Now, I know the memory bandwidth of the switch, so I drew up some numbers. I calculate how much like one particle takes up memory, and then how much I'm accessing that memory, how often, how many times per frame. And then plugging all these numbers in, I get that I should be able to draw 1,000,000 particles per frame, right? Which is not entirely unreasonable, right? The hardware is pretty damn fast. It's just that it's usually not utilized very well. Now, it is important to know that there will be some things like latency losses and stuff like that, some things you cannot maybe easily fix. But what this back of the napkin calculation tells you is that uh, most likely particles will not be a, like, memory bandwidth will not be a problem for your particle simulation. So if you maybe are running into problems when rendering only 1,000 particles, simulating and rendering only like 1,200 particles. This calculation means that it's probably not a memory bound issue. This is probably an issue with the amount of calculations you're doing. And then you can think about things like maybe I want to cut down on the calculations a bit. Maybe that will downgrade the quality of the particles a bit, but I know where to look, basically. I am pretty sure that this is not a memory problem, right? So, okay, the next thing that's worth knowing is that there will always be a bottleneck somewhere. So there is a point when you should probably stop, right? This is kind of relevant to the targets you're setting up for yourself. So if you're targeting 60 frames per second, once you reach that and it's stable throughout the game, right, there will be a bottleneck somewhere, but it's probably not needed to fix that, right? Because that bottleneck is not actually stopping you from running at 60 frames per second. So knowing your both targets from like game specification wise and time wise lets you have a better view of how to tackle the problems and whether you should tackle them or do something else about them. And yeah, probably the final thing I'd like to leave you with is to have reasonable defaults, because reasonable defaults are easy to optimize, right? I've run into a bunch of projects where the game had like no idea that it will have optimization, like performance problems, and then when you come down to the code and try to optimize it, you see that it's actually not that easy, and you have to like rewrite a bunch of things or tackle things that you didn't think you would have to tackle because these like the previous code owners didn't think about that. So having just a reasonable defaults helps with optimization down the road. Now there are a lot of things that could be said. What are the reasonable defaults, like, right? So probably two main things I would leave you with is avoiding big transform indirections. So that means like avoiding jumping through various branches, or maybe having very deep call stacks. And then that usually means like having less big, less wide, less high inheritance hierarchies, having like maybe more inline things, and then basically trying to minimize your vtable usage to not have to jump on like every single method or something like that. And then another thing which also helps with indirection is basically using arrays or batches or pools, something that is contiguous in memory, right? Because if we are caring about cache, well, the main thing that cache is doing is like helping with linear memory access. So if most of your code is accessing memory linearly pretty well, then helps you out in the long run because it is easy to drop in a replacement for array if it is too slow, but the array as a default will be fast enough. So yeah, that is it.